Okay, hello everyone. Welcome to again Bridge Math. So, uh, our topic for today is about numbers, which is actually a continuation of Module 2 in Bridge Math. Okay, so let's see what we're going to learn today. So, let's ask first, what is a number? Okay, a number is actually an item that describes a magnitude or a position. So we're going to learn more, about numbers today. So specifically, you're going to learn about the types of numbers. So you already know some types of numbers, right? Based on our modules. Then we'll know more about fractions as well as prime numbers. I'm sure you're familiar with prime numbers. And then other types of numbers as well. So those are our four main topics and objectives as today is to learn all of these four. Okay. Now, what are the type of numbers? Now there are actually two types of numbers you can say depending okay there are cardinal numbers. Cardinal numbers are numbers which allow us to count the objects or ideas in a given collection. So examples of cardinal numbers are 1, 2, 3, 4, 5, 103, 256, 900, 10,003, etc. So those are cardinal numbers. Now, another type of number is or are ordinal numbers. Ordinal numbers, on the other hand, state the position of the individual objects in a sequence. So very familiar with this. You are very familiar with this. So examples are first, second, third, fourth, 83rd, and 1689th. So etc. etc. So those are ordinal numbers. Okay, we also have several other concepts such as numerals. Numerals, they are symbols or combination of symbols which describe a number. So there are two main types of numerals. We have here the Arabic numerals. Okay. Arabic numerals were simply the modification of the Hindu-Arabic number signs and are written in Arabic digits. So example of Arabic numerals are 0, 2, 3, 4, 5, 6, 7, 8, 3,900, 42,343, and this number, I think it's actually 100,888,444. So those are numerals. So the other type of numerals are Roman numerals. Roman numerals, they are numbers which are written in Latin alphabet. So example of a Roman numeral is this one, MMXXII, which is actually 2022 or 2022. Okay, now I will upload a transcript later. So the transcript is actually contains actually links to several resources. So you can find other links in the transcripts. For example, in the Roman numerals, if you want to know more about Roman numerals, there's a link in the transcript. Okay. So next, let's move on to digits. What is a digit? Well, digit is a specific symbol or symbols used alone or in combination to denote a number. So it is a specific symbol or symbols used alone or in combination to denote a number. So examples of digits. So the number 1996 or 1996 has 4 digits. namely 1, 9, 9, and 6. Okay, those are digits. Okay. Now, before we go to irrational numbers, we already know about real numbers, right? In module 2. So now we're going to focus on irrational numbers. Okay. So common examples of irrational numbers are square root of 2, pi, and e. So what are the approximate values of these irrational numbers? So you can find them, okay, look for them for the approximate values. Now, for irrational numbers, there are actually several types of irrational numbers. We have the square root of primes, logarithms of primes with prime base, sum of rational and irrational, product of rational and irrational, infinite continued fraction, and special numbers. Okay, special numbers such as pi, Euler's numbers or E, and golden ratio. So those are special numbers. Now there's also a link in the transcript if you want to know more about irrational numbers. Okay. Now, next, let's move on to imaginary numbers. Now, if there are real numbers, then there are imaginary numbers. So our number system is composed of real and imaginary numbers. Okay. Imaginary numbers are denoted as I, which is equal to the square root of -1, or this symbol, square root of -1. It is also sometimes denoted as J. Okay, so here are the equivalents of imaginary numbers. So let's first look at the first line. So I again is equal to square root of -1, while I squared is equal to -1. I to the cube, or I cubed, or I to the third power is equal to -I. Negative I is also equal to negative square root of 1. Negative square root of -1, rather. Negative square root of -1. While I to the power of 4 is equal to 1. So those are samples of imaginary numbers, okay? Now, what are complex numbers? Or what is a complex number? A complex number is an expression of both real and imaginary number combined. So again, there's a combination of real number and an imaginary number. So it takes the form of a plus bi, a plus bi, where a and b are real numbers. So the variables a and b are real numbers, while I, you already know I, it's the imaginary number square root of -1, okay? Now, if a is equal to 0, then a pure imaginary number is produced. Okay, if a is equal to 0, a pure imaginary number is produced. If b is equal to 0, then a real number is produced. So just try it. You can substitute a and b into this equation, into this format, and you can produce several different types of numbers. Okay, so if you want to know more about imaginary numbers and complex numbers, there are links in the transcripts. Now, absolute value. What is an absolute value? The absolute value is actually the absolute value of a real number is the numerical value of the number neglecting the sign. So for example, the absolute value of -5 is 5. Okay, the absolute value of -x is x. So the absolute value, this is the symbol for absolute value. There's 2 bar. In the middle, there's a number there. So is either positive or 0, but can never be negative. Okay, so if you want to know more about absolute values, there's a link in the transcript, or there are links in the transcripts. Okay. Now, what are fractions? Well, you already know fractions. Okay, we discussed that, or you learned that in the modules. Now, there are actually several types of fractions. So, there are simple fraction, proper fractions, improper fractions, unit fractions, simplified fractions, integer represented as fraction, reciprocal fraction, or reciprocal, complex fraction, similar fractions, zero fractions, undefined fractions, indeterminate fractions, and mixed number. So let's see what are these types of fractions. So let's first look at simple fractions. Okay, simple fractions are, or simple fraction is a fraction in which the numerator and denominator are both integers. This is also known as a common fraction. Examples are 5 over 6 and negative 7 over 111. Okay, those are simple fractions. Now, let's go to proper fractions. Proper fractions is one where the numerator is smaller than the denominator. So example, 1 over 3, and then negative 7 over 12. So that's proper fraction. Now let's go to improper fraction. Improper fraction is one where the numerator is greater than the denominator. So that's 27 over 2. And we also have negative 99 over 7. Next, let's go to unit fraction. Unit fraction is a fraction with unity for its numerator and positive integer for its denominator. So examples of a unit fraction is 1 over 12,000 and 1 over 9. Okay, that's unit fraction. Next, we have simplified fraction. A fraction whose numerator and denominator are integers and the greatest common factor is 1. So that is a simplified fraction. So examples are 1 over 1,200 and negative 17 over 77. Okay. Next, let's move on to reciprocal. A fraction that results from interchanging the numerator and denominator, that is a reciprocal fraction or an operation. Okay. Examples. The reciprocal of 12 is 1 over 12. The reciprocal of negative 32 over 7 is negative 7 over 32. Again, the reciprocal of 12 is 1 over 12, and the reciprocal of negative 32 over 7 is negative 7 over 32. Now, let's move on to complex fraction. Okay. Well, a complex fraction, it is a fraction in which the numerator and denominator are both or both are fractions. So either the numerator or the denominator or both are fractions. So examples are 3 over 4 all over 1 over 17. Another example is negative 56 all over 3 over 7. And then last, we have 14 over 11 all over 79. Okay, those are complex fractions. How about similar fractions? Okay, similar fractions are two or more simple fractions that have the same denominator. Okay, So example, we have here 77 over 9, negative 39 over, negative 93 over 9, and 2 over 9. So they are similar fractions because they have the same numerator, which is what? 9. Okay. Now let's go to zero fraction. Okay, a zero fraction, it is actually a fraction in which the numerator is 0, and a zero fraction is equal to 0. Examples: 0 over 9, negative 0 over 22,001. So that these numbers or these fractions are equal to 0. Oops. Okay, let's move on to undefined. Undefined fractions, or an undefined fraction, a fraction with a denominator of 0. Okay, these examples here are an impossibility because nothing can be divided by 0. So 20 over 0 and negative 92 over 0 are undefined numbers or undefined fractions. Okay. Then let's go to indeterminate fraction. So indeterminate fraction, these are fraction which has no quantitative meaning. Example, 0 over 0, also infinity over infinity. It doesn't have any quantitative meaning. Okay. Now let's move on to finally the mixed number. Okay. Mixed number, a number that is a combination of an integer and a proper fraction. So we have 56 and 55 over 57, negative 9 and 851. So you can see there's a whole number part and there is also a fractional part. And remember, the fractional part should be a proper fraction. So that's a mixed number. Okay. Now let's move on to another topic. This is actually about composite number. So composite numbers are positive integers that have more than two positive whole number factors. So it can be written as product or of two or more integers, each greater than 1. So it is observed that most integers are composite numbers. So example of composite number of a composite number, 24 is a composite number because its factors are 1, 2, 3, 4, 6, 8, 12, and 24. So it has a total of 8 factors. Now, the number 1 is the only natural number that is neither composite nor prime. Okay. Now, speaking of prime, let's move on to prime numbers. So what is a prime number? A prime number is actually an integer greater than 1 that is divisible only by 1 and itself. Okay? So according to the fundamental theorem of arithmetic, every positive integer greater than 1 is a prime or can be expressed as a unique product of primes and powers of primes. Okay? Now, there is a special case. The number 2 is the only prime number which is an even number. Okay, if you want to know more about prime numbers, I included several links in the transcript. Okay. Now, what are the types of prime numbers? So let's see. We have here several types. We have natural prime numbers. We have twin primes. We have symmetric primes. EMIRP, relatively prime numbers, and unique product of powers of primes. So let's first look at Natural prime numbers. Natural prime numbers are those that have only two factors, 1 and the number. Okay, example of natural prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, and 23. Those are natural prime numbers that have only two factors, 1 and the number itself. Okay. Next, let's see what's next. Twin primes. So twin primes are a set of two consecutive odd primes which differ by 2. So what do we mean by that? Let's see an example. So first, we have here 3 and 5. They are twin primes because their difference is only 2. So 5 minus 3 is 2. So another one, 5 and 7. 5 and 7 are prime numbers, but they are also twin primes because their difference is 2. So 7 minus 5 is 2. Same thing goes for 11 and 13, 17 and 19, 29, 29 and 31, 41 and 43, 59 and 61, and 71 and 73. Okay. How about the next category? So we have here symmetric primes or Euler primes. So this word is actually read as Euler. Euler, like oil. So symmetric primes are a pair of prime numbers that are the same distance from a given number in a number line. So examples. So let's look at number 1. So number 1, it doesn't have a symmetric prime, as well as number 2, it doesn't have a symmetric prime. Number 3 don't have a symmetric prime. But the number 4 has a symmetric prime, 3 and 5. Why? Because 3 and 5 are the same distance from 4. So if you count 3, 4, and 5, they have the same distance from 4, 3, and 5. How about number 5? They also have a symmetric prime. 5 also have a symmetric prime, which are 3 and 7. So the distance of 3 to 5 is actually 2, and the distance of 5 to 7 is actually 2 as well. Okay. How about 6? The number 6, it also have a symmetric prime. Symmetric prime, so those are 5 and 7. So their difference is just 1. Okay, how about 7? They also have symmetric prime, which is 3 and 11. And you can compute for the differences or the distances, as well as for 8. Compute the distance of 5 and 11 from 8 and 3 and 13 from 8. So you can find your symmetric primes. Okay, now let's move on to EMIRP. So EMIRP or EMIRP is actually prime spelled backwards. So it is a prime number that remains a prime when its digits are reversed. And they can also be called reversible primes, which might include palindromic primes. So examples. So these numbers 11, 13, 17, 31, 71, 73, 79, 97, 101, 107, 113, 131, 149, 151, and finally 157, there are EMIRP or can be considered as EMIRP or reversible primes. Okay, why? Because if you reverse 11, still it is a prime number. 11, it's still 11. For 13, if you reverse 13, it will become 31, which is still a prime number. Same thing goes for 17, if you reverse 17, it will become 71, which is also a prime number. So they are IMIRP or reversible primes. But there are also palindromic primes that are reversible primes. Palindromic primes are prime numbers that when you reverse them, they still retain that number. For example, 11. If you reverse 11, it's still 11. If you reverse 101, it's still 101. If you reverse 131, it's still 131. And if you reverse 151, it's still 151. So it's not necessarily that EMIRPs are palindromic primes, but they are usually all reversible primes. Okay? Now, let's look at another category, which is relatively prime numbers. So relatively prime numbers are numbers whose greatest common factor is 1. Examples, 12 and 13. Their greatest common factor is 1. 13 and 11, and 77 and 23. Okay, their greatest common factor is 1, meaning they can only, both of them or both of these numbers can only be divided by 1. Okay? But relatively prime numbers, not for relatively prime numbers, not all the numbers need to be prime, like 12 and 77. 12 is not a prime number, 77 is also not a prime number. So they don't need to be prime numbers, okay? They are just relatively prime numbers. Relative to each other, they are prime numbers because they only have 1 as a greatest common factor. Okay. Next, let's move on to the unique product of power of primes. So, unique product of power of primes is a number whose factors are prime numbers raised to a certain power. So, example, okay, 360 is actually not a prime number, but it is a unique product of power of primes. So, 2, 3, and 5, those are prime numbers, and they are a product of powers. So 2 raised to 3 times 3 raised to 2 and 5 raised to 1. So these are unique product of power of primes. Okay. Now let's move on to the other types of numbers. We have here a perfect number. We're almost finished. Okay. So perfect number is an integer that is equal to the sum of all its possible divisors, except the number itself. So, for example, the factors of 6 are 1, 2, and 3. Now, when you add these factors, the sum is actually equal to the number itself. So, what do we mean by that? So, again, the factors of 6 are 1, 2, and 3. If you get the sum of 1, 2, and 3, 1 plus 2 plus 3 is actually 6. So those are perfect numbers. Again, except the number itself, okay? Except the number itself. Now, you can also look for other perfect numbers using this formula. So the formula for finding perfect numbers is 2 raised to p minus 1 multiplied by 2 raised to p minus 1. Okay. So 2 raised to p minus 1 quantity, 2p minus 1 quantity. Okay. Now, the conditions are p where p and 2p minus 1 should be prime numbers. Okay. So example. So we have here p is equal to 7. So in this case, 7 is a prime number. So check. We can use 7. How about 2 raised to 7 minus 1? So the 2 raised to 7 minus 1 is actually 127, in which 127 is a prime number. So check. We can use 7. We can really use 7. Therefore, we can get a perfect prime number. So in our formula, 2 raised to 7 minus 1 times 127, we can get the perfect prime number, which is 8,128. Okay? Now, we have here, let's move on to abundant number. Okay. What are abundant numbers? So abundant number is a number in which the sum of the possible divisors except the number itself is greater than the number. So example again, except the number itself again. So 18 has the following divisors. So 1, 2, 3, 6, and 9. And their sum is 21, which is greater than 18. That is why 18 is an abundant number. Again, actually 18 has another divisor, which is 18. So again, that is an exception, except the number itself. So if we get the sum of 1, 2, 3, and 9, that is 21, which is greater than 18, that is an abundant number, okay? Now, the opposite of abundant number is actually deficient number or defective number, which is a number in which the sum of the possible divisors, again, except the number itself, is less than the number. So, for example, 16 has the following divisors, 1, 2, 4, and 8, except 16 itself, and their sum is 15, which is less than 16. Okay, deficient number or effective number. Now, this is the last one. Amicable numbers or friendly numbers. So numbers can be friendly. So amicable numbers or friendly numbers refer to two integers where each is the sum of all the possible divisors except the number themselves of the other. So what do we mean by that? So the smallest known amicable numbers are 220 and 284. Why? Why are they friendly numbers? Why are they friendly numbers? So let's look at 220. The divisors of 220 are 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Okay, except 220, right? So if we get the sum of these numbers, their sum would be 284. While let's look at 284. The divisors of 284 are 1, 2, 4, 71, and 142. Now, the sum of these divisors is actually 220. So, did you get the pattern? 220, the same. 284, the same. So, that is why these numbers are amicable numbers or friendly numbers. So, other examples or other amicable numbers are 1,184 and 1,210, 2,620 and 2,924. We also have 5,020 and 5,564 and 6,232 and 6,386. So if you have extra time, you can look for other amicable numbers. Now let's have your final activity for this topic. So consider the following numbers. Give at least 5 facts about them based on the lesson about numbers. It is great if you try to use a variety in giving facts. Okay, be creative in giving facts, at least 5. So for example, 12. What is 12? 5 facts about 12. For example, it is an even number. And then it is a rational number. That's 2. And then 3, what is another, the factors of 12 are this and that. So at least 5. So you can give all the facts about these numbers based on our topic today. Okay. And that's it. So today we have learned about the types of numbers. We also learned about the different types of fractions and then the different types of prime numbers. And we also finally learned other types of numbers. Okay. So thank you. That's it. And again, don't forget to read or download the transcript for more details. Okay, thank you.